Let's do a super brief and informal introduction to the partial derivative and the gradient operator for physics. So you're probably wondering, what is a partial derivative? Suppose we have a multivariable function z being a function of the independent variables x and y. A partial derivative is a derivative of a multivariable function with respect to one of the independent variables. That derivative is evaluated while treating all other variables as constants. So for example, let's say we want to take the partial derivative of z with respect to x. We denote that by this fancy-looking, cursive-looking d. So this is the partial derivative operator. So the partial derivative of our function f with respect to x is denoted like this. And here, we can just say that we're treating y as a constant. You don't need to write that last part down. I'm just showing it to you right now so you can remember when you review these notes. If we want to evaluate the partial derivative of z with respect to y, well, that's found by evaluating the derivative of our function with respect to y, except this time we're going to treat all other variables, all other independent variables, in this case we have the independent variable x, as a constant. So in other words, when you take the partial derivative with respect to x, you treat y as a constant. And if you take the partial derivative with respect to y, you treat x as a constant. Now, I could say these words, but let's do a sketch or two to see what it looks like in practice. Let's draw an XYZ coordinate system. So we'll have the x-axis kind of going to the right. We'll have the z-axis be vertical. And we'll have the y-axis kind of pointing away from us. I'm trying to draw this with a little bit of perspective. And let's illustrate a three-dimensional surface. So in other words, a surface of a hill. So let's have a hill. It's kind of a funky looking hill, but that'll serve as a hill. So here's a hill in our three-dimensional space. And this hill, a point on the hill, or the height of a hill, can be described as a function of the independent variables x and y. So depending on where you are in x and y determines how high you are on the hill. Well, let's explore what it means to evaluate the partial derivative of our function with respect to y. Or rather, let's do the partial derivative of our function with respect to x. So the partial derivative of our function with respect to x is taken by treating all values of y, or by treating the variable y as a constant. So on our hill, let's just take a point in which we have y as a constant. So let's take a value of y equals b right here. And that value of y equals b describes a plane that is parallel to the z-x axis. So here's our plane right here. Now with our plane, that plane intersects the hill, and that intersection is going to create a curve of intersection that might look something like this. Now this curve of intersection is generated by treating the value of y equal to the variable b, or equal to the constant b. So z now is a function of x. It's a function of x where y is equal to the constant b. So now let's say we want to find the derivative at a point on this curve of intersection. Let's take a point, an arbitrary point, to be maybe right here on the curve of intersection. Now the slope of the tangent line at this point will be equal to our derivative at that point. So at that point on our hill, let's just drop a line to the xy plane and then a line to the x-axis. This corresponds to the value of x equals a. And the slope of our tangent line at that point is equal to the partial derivative of our function. In this case, remember, since y is a constant, this is our function of x with respect to x, where y is our constant, and that is going to be equal to the slope of our tangent line on our curve of intersection between the plane y equals b and our hill. If we take a different point on this curve of intersection, we may have a different slope. But this is still found by evaluating the partial derivative of z with respect to x. Well, now, what if we want to treat x as a constant and find the partial derivative of our function with respect to y? Let's see what that looks like by drawing another sketch. We'll keep to the same coordinate system where the z-axis is up, the x-axis is kind of going to the right, and the y-axis is kind of going away from us. Let's use the same hill. So here is our hill. Well, it doesn't quite look the same, but that's okay. There is our hill. This hill is described by the same function z as a function of the independent variables x and y. But this time, we want to evaluate the partial derivative of z with respect to y. That partial derivative of z with respect to y will be found by treating x as a constant. So we'll just pick a value of x. We'll say a. We'll treat the value of x as a constant while allowing y to vary. So in other words, x is a constant. And let's look at an equation of a plane, or let's look at a plane that is parallel to the zy axis with the equation x equals a. So this is the value of x equals a. And that plane slices through our hill again, like that. Now, if we were to look at the curve of intersection here, that curve of intersection might look something similar to this. This curve of intersection is described by the function x equals a, allowing y to vary. So we now have our equation for our curve of intersection. It is essentially our function of f holding x constant. And so if we want to evaluate the partial derivative at a point on this curve, let's take a point right there. That is going to be equivalent to the slope of the tangent line on that curve of intersection. Now, that slope of the tangent line at a point, we'll just say that that occurs at, well, I'll drop this down. We'll say that that point occurs at the value of y equals b. Let's choose a different perspective to view this curve of intersection and the slope of the tangent line at that point. We'll do this by looking down from the positive x-axis. Looking at from the positive x-axis, the y-axis would be to the right, the z-axis is vertical, and our hill looks something like that. And our curve of intersection looks something like that. This corresponds again to z as a function where x is a constant a, so z is a function of y. And evaluating the partial derivative at a point on this curve is equivalent to calculating the slope of the tangent line at that point. And we'll say that this is the value of x equals a, y equals b. So a partial derivative with respect to an independent variable of a multivariable function is just simply the derivative of that function with respect to one of the independent variables, while treating all of the other independent variables as if they were a constant. In essence, we're just evaluating the derivative at a point on the curve of intersection between a plane that is parallel to one of the coordinate planes and our surface.